Welcome to this presentation on Laplace transforms. In this short presentation we're looking at initial and final value theorems. An overview of the presentation here. I'm going to commence by just reviewing the table of standard Laplace transforms we've seen before. I'm going to describe the initial value theorem and look at worked examples. I'm going to describe the final value theorem and again look at some worked examples. I'm going to leave you with some tutorial questions. The Laplace transform table, as here standard tables we've seen before, just given for reference, and we'll be referring to these in the examples that follow. The functions of t highlighted in dark red text there are ones that have been proved on a previous presentation. Continuation of the table there, again some of those transforms we'll be reviewing later on. Okay, going to mention the initial and final value theorems. Going to start with the initial value theorem. There are several theorems in Laplace transforms that are used. They help simplify and interpret solutions to certain problems. It's normally involving systems type work. Two theorems we're going to look at are the initial and final value theorems, and these theorems are used in such things as pulse circuit applications, where response of the circuit for small periods of time or the behaviour immediately after a switch is closed are to be investigated. So the initial value theorem will be the first theorem we will look at here. Now on the left hand side of the equation we've got the limit of the function of t. Now in the initial value theorem we consider this as t tending towards 0. So time tending towards 0. On the right hand side we've got the Laplace function and the limit there for the Laplace function, which is s times the Laplace transform of the function of t, is s tending towards infinity, and we'll think of infinity being just a really big number in the work we're going to do. Example 8 here, we're going to verify the initial value theorem for a function given, and we're going to state its final value. Now the function of time given here is 3e to the 4t, and we're going to first of all start off by finding the Laplace transform of 3e to the 4t. Now e to the 4t is a standard form in the tables. If you look it up it'll be 1 upon s minus a, so it's 1 upon s. In this case the a is 4, so it's minus 4 for the Laplace transform, and of course in this particular instance we're factoring by 3, we're just multiplying by 3. So the Laplace transform for 3e to the 4t will be 3 upon s minus 4. Now using the initial value theorem here, on the left hand side of the equation our limit for the function of t, the time domain, is tending towards 0. So what we will do here is we'll simply put the value of t is equal to 0 wherever we have a t in our function, so it will be up here. So the function we're given is 3e to the 4t, and we're looking at when that tends to 0. If you put the 0 in for the t, we basically get e to the power 0, and anything to the power of 0 is 1, so we end up with 3 times 1, 3 on the left hand side. On the right hand side, which is in the Laplace domain, we've got an equation to deal with here. Is s times the Laplace transform of the function of t, and s tends to infinity. So just a bit of expansion here of the brackets. I'm going to multiply the s by the 3 upon the s minus 4t that we have above in the Laplace transform. And then we're going to make the s tend towards infinity. So if you just look at the arithmetic here, basically we end up with the infinity times by the 3 upon infinity take away 4, and again just think of infinity as being a really big number, so in effect that's really going to be infinity times 3 divided by infinity, because infinity take away 4 is still a really big number. So the infinities effectively cancel on the right hand side and again give us 3. So we've shown that we can get initial value from this theorem of 3. Okay, example 9 here, we're asked to verify the initial value theorem. Again here for a particular function that's given to us as a function of t, and we've got to state the initial value from the solution. So the function of t in this case is 7t minus 4 sine 2t, and we can use our standard Laplace transform table to find the transform for these functions. So taking the Laplace transform of the 7t, t in the Laplace transform table is 1 upon s squared, which of course we're multiplying by 7 here, and then we're taking from that the Laplace transform of the sine of 2t. Now if you look in the tables, that will be a upon s squared plus a squared, In this case the a is equal to 2, and we're of course multiplying that by 4. So just to simplify the terms here, we'll end up with 7 upon s squared is the first term, and that's the Laplace transform of 7t, and we're taking away 8 upon s squared plus 2 squared, and that's the Laplace transform for the 4 sine 2t. Again, we're going to apply our initial value theorem here, where on the left hand side in the time domain we're going to let time tend to 0, and on the right hand side, the Laplace domain, we're going to let the s tend to infinity. On the left hand side of my initial value theorem, I've got the limit of the function of t, which will tend to 0. On the right hand side of the initial value theorem, I've got limit of s times the Laplace transform of the function of t, and s will tend to infinity, this large number. Now, just sticking with the right hand side of the equation here, I'm just going to expand the brackets effectively. So I've got s times 7 upon s squared simplifies to 7 upon s. I'm adding to that, I've got s times the 8 upon s squared plus 2 squared, so that gives me 8s upon s squared plus 2 squared. Okay. If I go to the left hand side, I'm going to put the value of t now tending to 0, so I'm just going to put a 0 wherever I see a t. I'm going to place a 0 instead, so I get 7 times t becomes 7 times 0, so that goes to 0, and 4 times the sine of 0 also goes to 0. So the left hand side of the initial value theorem is showing me 0. If I move back to the right hand side and now I put my s tends to infinity, just think if it's a large number here, then 7 divided by that large number will tend to 0, and on the next part of the equation I get 8 times the infinity over infinity squared plus 4. That could really be stated as 8 times infinity over infinity squared, because the plus 4 would be irrelevant to a really large number, and if you want to cancel the infinities top to bottom, I would get 8 upon infinity. Effectively 8 divided by a really large number, it tends to 0, so the right hand side also tends to 0. So initial value of this system is 0. Example 10 here, again we've got to verify the initial value theorem again, given a function. Now just be careful with this function as it's given, because it's not in standard form. 3t plus 4 all squared is not a standard form. It's not something we can look up in our Laplace transform table, so be careful here. Given that function of t, the first thing I need to do is expand the bracket. And don't forget that's a binomial bracket. That is 3t plus 4 multiplied by 3t plus 4. Okay, so expand it as a binomial expansion. So if we do that, we'll get 9t squared plus 24t plus 16. If you're not sure about that, I would encourage you to check the binomial expansion. We're now going to find the Laplace transform of the 9t squared plus 24t plus 16. Now when you look at the terms here, we've got 3 functions here. We've got a t squared, we've got a t, and a constant. If you go to your Laplace tables, you will see for t squared, the Laplace transform is 2 factorial over s cubed. If you look for your Laplace transform of t, it is 1 over s squared, and if you look for the Laplace transform of a constant, it is 16 upon s. Obviously in this case we're multiplying by, in the first term multiplying by 9, so 9 times factorial 2, don't forget factorial 2 is 1 times 2, so 9 times 2 gives us 18 upon s cubed, 24 times 1 upon s squared, and then the 16 upon s. So there's our Laplace transform for this function of t. Okay, on this slide I'm just repeating the line from the previous slide here for convenience. We're going to apply the initial value theorem here, so on the left hand side, limit of the function of t, t is tending to 0. On the right hand side, limit of s times the Laplace transform of the function of t, and s is tending to infinity. If I just works with the left hand side first of all, this is our time domain here. I'm basically going to put the value of t equal to 0 wherever I see a t in my expression. So I've got a t here and a t here, so I'm just replacing that with a 0 and a 0. So obviously 9 times 0 squared is 0, plus 24 times 0 is 0. I get left with 16 on the left hand side of the equation. If I go back onto the right hand side of the equation, I'm going to expand the bracket here with the value of s here. So I've got s times 18 divided by s cubed, so that simplifies to 18 upon s squared. I've got s times 24 divided by s squared, that simplifies to 24 upon s, and I've got 16 divided by s times by s, that simplifies to 16. If I put my limit in of s tending to this really large number, I've got 18 divided by a really large number, so that tends to 0. I've got 24 divided by a really large number, again tending to 0, so that leaves me with 16 on the right hand side. So the right hand side shows 16 as well. So the initial value for our system is given as 16. Okay, we're going to look at the final value theorem here. The final value theorem is particularly useful when looking at stability of systems. Example given here is automatic aircraft landing systems, and is generally concerned with the steady response of the system for large values of time t, when all the transient effects have diminished. Often when you switch a system on initially, there are what are called transient effects, kind of variable effects that occur, but after these dissipate, we get into the steady state response, and often that's the part of the system that we're particularly interested in. So for the final value theorem, in the time domain, the limit of the function of t, now t tends to infinity, to a large duration of time, and on the right hand side, the limit of s times the Laplace transform of the function of t, the s times to 0 tends to 0 here. Okay, example 11, we're going to verify the final value theorem here for a function we used in the previous example. So our function of t is 3e to the minus 4t. In the previous example, the Laplace transform of 3e to the minus 4t was shown to be 3 upon s plus 4. That's from our standard Laplace transform tables. We're going to apply the final value theorem this time. So on the left hand side, our limit of function of t is tending to a large duration of time, we'll call that infinity. So in this case the limit is of the function of t 3e to the minus 4t. We're going to put the value of t equals infinity. Now just think this through here. We're putting the value of infinity for the t, so we've got e to 3 times e to the minus 4 times infinity. In other words, e is raised to the power of a very large value, but don't forget we are dividing by that value because of the negative index. So really we've got 3 divided by e to the power of a very large number. So basically what happens there is 3 is divided by the infinity, this large number, so it tends to 0. So the left hand side tends to 0. If we go back to the right hand side in the Laplace domain, we've got limit of the s times the Laplace transform of t. This time s is going to tend to 0, so we're going to put a 0 wherever we have an s, and straight away we can see the whole term disappears. If we put a 0 for the s, then this whole term will disappear because we're multiplying the bracket by 0, so it completely disappears, and the left hand side is 0. So this illustrates the final value theorem, shows a value of 0 for this function. Example 12 here, again we're going to verify the final value theorem here. We're given a function, 5 plus e to the minus t times sine of t, and we're going to find the final value of this function using the theorem. So our function of t is 5 plus e to the minus t multiplied by the sine of t. I've included an extract here from the Laplace transform table just for convenience. It shows the 2 Laplace transforms we're interested in this example. First one we're going to interest is a constant. When we find the Laplace transform of a constant, it simply becomes the k upon s. And if we've got a function e to the at multiplied by sine omega t, we're told that the Laplace transform is omega upon s minus a all squared plus omega squared. So if we look at our Laplace transform of the functions given here, the 5, which is a constant k in the above table, simply becomes 5 upon s. And we're adding to that in this case the e to the minus t sine t. Now notice in this case the a is going to be minus 1 because we've got a minus 1t, e to the minus 1t there, and the sine value, the omega in the sine value would be 1. It's sine of 1t. We don't write those the ones, but they're there. Okay, so in this particular case we need to be careful. The a is equal to minus 1 and the omega is equal to positive 1. So again, be careful how you put it into the Laplace transform. Is s take away, that's in the Laplace transform, but our a value here is minus 1, and our omega value here is positive 1 and here. So that simplifies the next line of 1 upon s plus 1 all squared plus 1. Just be careful there of the directed numbers, the double negatives there. Continuing the solution over the page, we're going to apply the final value theorem. As I said before, on the left hand side in time domain, the t is now going to tend to infinity. On the right hand side in the Laplace domain, we've got s times the Laplace transform of the function of t, and s is going to tend towards 0. If I just stay with the left hand side first of all, what we're going to do basically is put the value of t tending to infinity wherever we see a t value. So I see a t value here and a t value here. Okay, so we get 5 here. The 5 is not affected by the t, it's not a function of t, so that stays as 5. But this value here is e to the minus infinity, and again what we're saying there really, it's 1 upon e to a very large number, so you're dividing 1 by a really large number, so that will tend to 0, so that whole term will disappear. Alright, so we'll be left with 5 on the left hand side, and the sine function completely disappears because it's being multiplied by 0. So 5 is on the left hand side. For the right hand side of the equation, we go back to here. The first thing we should do is expand our Laplace transform by the s. So s times 5 upon s will simplify to 5, and then s times the 1 upon the s squared plus 1 all squared plus 1, that will give us s upon the s plus 1 all squared plus 1. Again, if we put our limit in, the limit here is the s tending towards 0, the 5 remains as 5 because it's a constant, it's not affected by the s value, but we put an s of 0 into the next expression, so the whole term then will disappear because we're dividing into 0. So again, on the right hand side, we end up with 5. So the final value for this system is 5. A question for you to leave with you, it's very similar to the previous example. If you want to run through that, I would encourage you to do so, and also a few further problems that look at both the initial value and the final value theorems if you want to attempt them. The answers are in brackets. Thank you for viewing.